well, but the versions of them we've seen now, of course, is the discrete that we talk about today, and then we'll see the continuous ones next week. Let's see. Specific distributions. We are going to meet 3 now. And the first one is hopefully, most likely, a well-known one to you. We're going to meet those 3, and we're going to start with this one, because now we have talked about the general constructs of probability. To work with such probability models for real life situations, we need specific distributions to be able to work with them. So, the binomial, let's recap. Basically, it is like having repeated coin tosses, right? So the binomial distribution is the distribution that is going with throwing a coin. That's how we can remember it, right? We are talking about independent repeats of sometimes it's called a binary or a Bernoulli experiment with 2 possible outcomes, success or failure. No handicap or handicap, if we are looking at the kid's example from the beginning. If we have such a case where we do that, a number of repeated success-failure experiments, we can, if we are then interested in, that's the point, that's the kind of the situation we decide that we are in. I'm not really so much interested also about the kids. I'm not interested in which order these 70,000 babies were born, and when I had a handicapped and when I did not have a handicapped over the year. For now, I'm just interested in the number of handicapped children across over the whole year. I don't care about in which order they came during the year. I'm just interested in the number. Then we use this typography, these letters, this syntax, to express the following fact, that in such a case, the probability function, the density function, looks like this. With this funny construct, the n over x, it's not a fraction, it's not n divided by x, it has a very specific meaning. It's the so-called binomial coefficients. In R, it's simply called choose. And then you have to provide the n and the x, and you have an R function giving you this value. You would also have, you remember the factorial? Well, 3 factorial equals 3 times 2 times 1, and the R name of the function is, funny enough, factorial. Let's just spend the last minutes here, or some minutes, on recapping why the heck we have something like this, and not really proving everything, but still just making an education of why the probability looks like this. Let's think about a case where n equals 3. Let's think about the possible outcomes if I throw a coin 3 times, right? I could have, should I call it success, success, success? I could have success, success, failure. How many are there? If now I'm suddenly, if just for a second, I'm back at where I'm actually interested in the order, just to know exactly what could happen in this system. So yeah, what would you think? 8 possible ones, I agree. Let's see what happens. Let's try to write them up, all of them. Success, failure, success, success, failure, failure. Then I had the 4 S's, and I have the same ones, just with the F on the first place. And I have basically F, S, F, 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 S, and F, F, F. Let's count the number of successes in these 8 possible. That's the only thing that can happen. Let's also, let me just count the number of successes. That was difficult. 3 successes, 2, 2, 1, 2, 1, 1, 0, right? Let's also, for the ease of it, assume for now that the individual probability of success is 50-50. That need not be the case, of course. We can handle asymmetric coins. We can handle the fact that a probability of an individual baby becoming getting some handicap is, of course, not a 50-50. It's luckily enough only around 5% probability. We can handle that. But let's, for the ease of it, just think of p equal 0.5 now. If I should use this table to put the probability of seeing, for instance, exactly one success among these 8 possible outcomes, well, then I would say I should have a success 1 time. I should have a failure 2 times. This is the independence of events that I use here. 1 time success, 2 times failures. And now I do the general one instead of just plugging in the half, just to make a point here. But then I see that this happens actually. 1 success happens, this one happens more than once. It happens 3 times, right? It can come the first, it can come second, it can come third. So I have to count these times that it can happen. If I were going to have 0 successes, if I'm going to count that one, it can happen in only one way. Then I need 3 failures and 0 successes, p to 0, 1 to 1 minus p to the third, and then counting in how many ways could that happen? Well, only one way, that is failure, 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 right? The counting is what we do here. So this is a combinatorial thing, this choose thing, this binomial coefficient. This is the name, and those factorial ones, I'm not going to try to argue why that's the right thing now. That's combinatorics, and we can leave that for the exercises if you want. Or you can just accept it, or remember that maybe someone explained it to you previously. The thing is, it's a bit difficult if I'm going to count in how many different ways can 3,000 handicapped babies come in a sequence of 70,000 births. If I start doing this exercise, I started here, I'm going to spend a few years doing that. I'll have 3,000 failures and then 67,000 successes. That's the first outcome. Then 2,991, one step further, one step further. Okay, those come 67,000 times almost. And then I have to just move the next one. It's a pretty combinatorially advanced thing to try to count. Someone did that counting for us and put it into a formula like that, the n over x, right? So that's good. That's the binomial probability function, and we are going to be able to work with that. As an example, before the real example, but let's look at this one. We are trying to actually do it, sort of relative, little example here that could be linked with the dice example. For instance, down here, if I sample, so I'm doing the dice thing again, the fair dice. I sample 30, I throw the dice 30 times. However, now I only count the number of 6s, so I choose to look at the system where I just say either it's a 6 or it's not a 6, right? If I look at it this way, and that is counting 6s, I can describe that system also as a binomial system, as a coin-tossing system. And doing that would in a way simulate a binomial outcome. Let's try to do that. Whoa, to be careful about this stuff down here if I want to survive. Let's try to jump into R. The first one, which has sort of jumped on the slides, let's do it anyway. I didn't dwell on that on the slides. Let's just try. The underlying probability of success I set at 10%. I try to do 30 coin tosses. I could do it like this. I could sample the two numbers 0 and 1. The C01 is, I sample from the 0 and 1. I do it 30 times. I use the p and the 1 minus p. The p goes with the 1 minus p goes with the 0. So there's a probability of 10%, 0.10 to get the 1 and a 90% to get the 0. That would give me a binomially distributed number. In this case, it came out 4. Let's see what happens. If I do it many times, 3, 1. Remember, I do it out of 30. But there's only a 10% chance to get something. So what is the expected number of outcomes when I 30 times do something with a 10% probability? How many would I expect on average to get here? Yes, please. 3. Does it add up? 2, 4, 2, 1, 1, and then I missed it. Yeah, anyway, it looks to me it looks pretty much okay. It doesn't give me 3 every time, right? But on average, probably it looked to be quite close to 3. Anyway, we don't have to do it this awkward way. Such simulation functions are already built into R for us. So there is an R binom function that is random binomial numbers coming out. We're going to get back to this because you might wonder, but I'll not explain to you until a few weeks from now. There is not a small guy sitting in the computer throwing the dice for us. It's another way that the computer makes random numbers to us, but we'll get back to that. I hope you can accept that the computer is able to do something that appears as random numbers, at least. For some of you, it's not magic. For others, it might be magic. We can just run this one. 2, 4, 2. Doesn't seem too different from the average of 3, which was nicely said. What I just showed you on the slide was this fair dice example. For instance, number of 6s, 8 6s out of 30 throws. I could also simulate that by the R binom function. I could go 30 throws with a probability of 1/6 with the R binom, and then I could count. How many 6s do I get? How many 6s do I get? When I throw 30 times, that would then be 1/6. That would be more like average 5, I would say, right? 30 divided by 6, that's average 5. Right? So that was just playing around with the binomial probabilities and seeing that the functions are there for us to play around with it. Right? Any questions so far? Before I leave you for the break, some of you may have seen, but I did actually prepare. You can use the last minute or two, and then during the break, if you like, if you want to play with me again. I did put in another little quiz. It's mostly me wanting to know about whether you did your homework, okay? I did put it completely anonymous this time, so don't worry. I don't see your names. I don't care about your names. It's a free country. I only care about all of you doing good in my course. And the only way we test you is by the project reports, and the exam will give you the final grade. The project reports is just to allow you to go to the exam. So the only way you're judged, evaluated, is the final exam. So don't care about showing to me or any and the TAs that you might not understand everything, because to say it a bit roughly, I don't fucking care. Understand me correctly. I would like all of you to understand as much as possible. Whether you as an individual have a problem, it's not a problem for me, right? And I'm not going to judge you by that in any way. So don't worry about that. Just try to learn it, right? And if you all learn it and you score top on the exam, I'm a happy guy. That's my purpose, right? So play with me if you want. There's a little thing, and then a little end thing at the end. And it's the Socrative, and it's still the same. I should say, it doesn't say here. It's still, like last time, my initials, my first name and my initials, per BB, that you need to log in the room with that. And then we'll have a look at the end, how it goes. At least on the last one. I mean, the first one is basically mostly for me and for you, maybe. Anyway, let's start again. 9 exactly, according